Hello everyone, this is lecture 26 of the subject analog circuits. In this class, I am going to discuss the inverting amplifier and non-inverting amplifier, summer circuit, integrator and differentiator. So, starting with the basics of the inverting amplifier. In inverting amplifier, the input signal is applied at the inverting terminal, right. So, in the last class I had discussed the basics of operational amplifier, there I had discussed this inverting and non-inverting amplifier. In this class, firstly we are going to derive the output voltage equation for inverting and non-inverting amplifier. So, in inverting amplifier, the input signal is applied at the inverting terminal, this non-inverting terminal is grounded and a resistor is connected at the inverting terminal and there is a feedback resistor RF is connected between the output and the inverting input terminal of the op amp. Let us say this is the input voltage V in and this is the output voltage V naught and this resistance input resistance is R 1. So, this is the inverting amplifier. So, you can see that this is the closed loop configuration of op amp. Op amp is in negative feedback, that is required for the amplifier. Now, by considering that the op amp is the ideal op amp, so virtual ground is going to be applied. Or in virtual ground concept, what happens? The voltage at the non-inverting terminal, it is equal to the inverting terminal, right. Let us say this is node A. So, the voltage at the node A, it will be 0 volt, right. This node A is called the virtual ground, because this node is not connected directly to the ground, but since the open loop gain of the op amp is very high, that is why the voltage at the non-inverting terminal is equal to the voltage at the inverting terminal, right. So, this concept I had discussed in the last class also. And next consideration which we are going to take, that is the current entering the op amp is 0. It means that no current is entering the op amp, no current is entering the op amp, because the input resistance of op amp is very high, ideally it is infinite. So, if the resistance is infinite, that means that there is no current, right. It means that if the current flowing through this R 1 resistor is I 1, so the same current will flow in the feedback, because there is no current entering the op amp. So, if we apply KCL at node A, then what will happen? The current flowing through resistance R 1, it will be equal to V in upon R 1, incoming current is equal to outgoing current. So, we are just applying the KCL at node A. So, the feedback current, it will be equal to, let us say the voltage at node A is V A. So, it will be the V A minus V naught upon R F, right. The feedback current, it will be equal to the voltage across this R F resistance upon this R F value, and one terminal of R F is connected to node A, that is the potential of node A is V A, and the another terminal of R F is connected to output voltage V naught, and by virtual ground this V A is 0. So, from here what will be the output voltage? V naught will be equal to minus R F upon R 1 into V. So, what will be the voltage gain of this inverting amplifier? It will be equal to minus R F upon R 1. This voltage gain is your V naught upon V in, right, and this gain is the closed loop gain, because we are calculating this gain in closed loop configuration. So, you can see that the gain is negative. Negative gain means the output is 180 degree out of phase with input, output is 180 degree out of phase with input. Now, what will be the input resistance of this circuit? The input resistance, it will be equal to input voltage upon input current, that is equal to R 1. So, the input resistance is R 1 and of course, the output resistance is 0, resistance seen at the output terminal, it is 0. Now, see, since the input resistance is R 1 and we want higher input resistance for voltage amplifier. So, if we increase the value of R 1, then your voltage gain will be reduced. So, the limitation of this inverting amplifier is that the input resistance is very limited. To remove this drawback, we use non-inverting amplifier. In non-inverting amplifier, now the input signal is applied at the non-inverting terminal, and at the inverting terminal there is a resistor R 1 connected and one terminal is connected to ground. There is a feedback resistance R F, this is output voltage V naught. Again you can see that this is the closed loop configuration in negative feedback, right. Now, again we have to calculate the voltage gain of this non-inverting amplifier, that is V naught upon V. Again considering the ideal op amp, it means that the current entering the op amp is 0, and by applying the virtual ground, the voltage at the inverting terminal, it will be equal to V in, because the voltage at the non-inverting terminal is V in, that is the input signal that is directly being applied at the non-inverting terminal. So, the voltage at the inverting terminal, it will be V in, and let us consider this node A. Again apply the KCL at node A, right, apply the KCL at node A. Let us define the current direction, let us say its current is I, this current will be I again, because the current entering the op amp is 0. So, applying the KCL at node A, what will be the equation? Incoming current is equal to outgoing current. So, it will be V naught minus V A, V A is the voltage at the node A upon RF is equal to V A minus 0 upon R 1, because the another terminal of R 1 is grounded, right. This V A is equal to V in, this V A is equal to V in. So, from here we can calculate the value of V naught upon V in, and that is equal to 1 plus R f upon R 1. So, the voltage gain of the non-inverting amplifier is 1 plus R f upon R 1, and important thing is that this gain is positive. Positive gain means output is in phase with input. So, when we apply the input signal at the inverting terminal, then we get the negative gain. When we apply the input signal at the non-inverting terminal, we get the positive gain, right. And what will be the input resistance of this non-inverting amplifier? Since the input signal has been directly applied at the non-inverting terminal and the current entering the op amp is 0. So, the input resistance is infinite, because the current at the non-inverting terminal is 0, current entering the op amp is 0, and the input signal is applied directly at the non-inverting terminal. So, the input resistance is infinite. So, that is the advantage of non-inverting amplifier over inverting amplifier, the input resistance is higher for non-inverting amplifier. For non-inverting amplifier, the output resistance is again 0, it is about input resistance, the input resistance is higher for non-inverting. Now, one of the application of the inverting amplifier is the summer circuit, adder circuit. We can add 2 voltages or more than 2 voltages using the inverting configuration of op amp. We have already seen the inverting configuration of op amp. So, in inverting configuration of op amp, the non-inverting terminal is grounded, and at the inverting terminal there is a resistor connected, let us say it is R 1, and in the feedback there is a resistor, that is R f. This is the output voltage V naught, and this is the input voltage V 1. Now, if we want to add 2 voltages, if we understand how we add 2 voltages, we can understand it for 3 and 4 voltages and for more than 4 also, right. So, let us consider the simplest case, addition of 2 voltages. So, the first voltage is V 1, the second voltage is V 2. Again this V 2 will be applied to the inverting terminal through a resistor, let us say it is R 2 and it is connected to the inverting terminal, right. Now, again the same thing, let us consider this is node A. We need to find out the value of the output voltage V naught. For that again we will apply the KCL at node A. Now, consider the current flowing through the R 1 resistor is I 1, the current flowing through the R 2 resistor is I 2. Considering the ideal op amp means the current entering the op amp is 0. So, it is 0. So, what will be the current flowing through the feedback resistor? It will be equal to I 1 plus I 2, I 1 plus I 2, right. So, to find out the output voltage, just apply KCL at node A. So, what will be the value of I 1? I 1 will be equal to V 1 upon R 1, right, and of course, the voltage at the node A is 0 because of the virtual ground. So, this V 1 upon R 1 plus V 2 upon R 2, it will be equal to voltage V A minus V naught upon R f, and this V A is 0, Now, from here what will be the output voltage? The expression it can be written as minus of R f upon R 1 into V 1 minus of R f upon R 2 into V 2. If we take this minus sign common, then it will be R f upon R 1 into V 1 plus R f upon R 2 into V 2. If we consider R f is equal to R 1 equal to R 2, then what will be the output voltage equation? It will be equal to minus of V 1 plus V 2. So, it means that output voltage it is the summation of two input voltages V 1 and V 2, right. This minus sign it just represents that the output is 180 degree out of phase with input. Otherwise, if we consider the magnitude part, then the output voltage is just the summation of the input voltage. So, similarly, if we want to add 3 voltages, then we need one more resistor R 3, right. So, by using the same approach we can add n number of voltages. So, this is called the adder circuit. So, you can see that this is the application of the inverting amplifier. Next one is the application of the non-inverting amplifier. Like we have already seen the non-inverting amplifier. So, there are many applications of non-inverting amplifier. One of the application of non-inverting amplifier is the voltage buffer circuit. Voltage buffer circuit. How we design this voltage buffer circuit? Let us again draw the circuit of non-inverting amplifier. This is your V in, this is V naught, this is R 1 resistor, in the feedback there is a RF resistor. So, this is the non-inverting amplifier. If in this non-inverting amplifier, if we put R 1 equal to infinite, RF equal to 0, feedback resistance is 0, 0 means short circuit. So, this non-inverting amplifier, the circuit it will be like this. Now, the output will be directly connected to the inverting input terminal. Now, in this case what will be the output voltage? It will be V naught will be equal to V in, because the voltage gain for non-inverting amplifier is 1 plus RF upon R 1. This RF is 0. So, the voltage gain will be 1. Voltage gain is 1 means output voltage is equal to input voltage. So, the in voltage buffer circuit the output follows the input, that is why it is also called voltage follower circuit, right. So, this is your voltage buffer circuit or voltage follower circuit that we have designed using op amp. We have already designed this voltage follower circuit using BJT, using MOSFET in unit 1, right. So, this is one of the application of non-inverting amplifier, and for this voltage buffer circuit you can see that the input resistance again it will be infinite, because the input signal it has been directly applied at the non-inverting terminal, right, and the output resistance is very low. In ideal case R naught is 0, that is required for the voltage follower circuit. For voltage follower the input resistance should be high, output resistance should be low, in order to avoid the signal loss, in order to tackle the problem of the loading effect, right. Now, another application of inverting configuration of op amp is the integrator. Integrator is a circuit which integrates the input signal. It mainly utilizes the inverting configuration of op amp. So, in inverting configuration of op amp that we have already studied, again draw the circuit of inverting amplifier. This is the input signal V in, and there is a feedback resistor RF and input resistor R 1. Now, if in this inverting amplifier circuit, if we replace this feedback resistor with capacitor, then it will become a integrated circuit. So, the basic concept if we understand how we are designing this integrator and differentiator circuit, the voltage gain equation V naught upon V in, that is equal to, actually it is minus RF upon R 1, that we can write it as minus Z 2 by Z 1. Z 2 is the impedance of the feedback path, Z 1 is the impedance at the input side, minus Z 2 by Z 1. For integration, integration means in S domain, in the equation there will be 1 by S term. So, we want a circuit in which there should be 1 by S term. So, how we can get that 1 by S term? If this Z2 is a capacitor, if Z2 is a capacitor, then we know that the impedance of the capacitor is 1 by SC. So, you can see that if Z2 is capacitor, means feedback is a capacitor, then the impedance will be 1 by SC, there we will get the term 1 by S. So, the point is that by understanding these things, we come to know that if we connect a capacitor in the feedback, then it will become integrator, fine. So, it means that the circuit for the integrator, it will be at the input there will be a resistor, this is your input signal V in, and in the feedback there is a capacitor C, and this is the output voltage V naught. So, we have already calculated the value of V naught upon V in, that is equal to minus Rf upon R1, that can be written as minus Z2 by Z1. Z2 is your capacitor, so it can be written as minus of 1 by SC. The impedance of capacitor is 1 by SC upon Z1 is R1. So, it is R1. So, V naught upon V in is equal to minus 1 upon SC R1. Again there is a minus sign because the input signal is applied at the inverting terminal. Whenever the input is applied at the inverting terminal, the output will be negative. So, you can see that there is a 1 by S term in this equation that represents the integration. This is the frequency domain equation. For time domain equation, you can derive it. Considering this is node A, what is the potential at node A? Obviously, it is 0 volt. If we are considering the ideal op amp, so in ideal op amp what is happening? In ideal op amp, the current entering the op amp is 0, virtual ground is being applied, right, because of the infinite open loop gain. So, it means that if the current flowing through resistor R1 is I1, then the current flowing through the capacitor will be I1. Again apply the KCL at node A. So, these things I have already discussed. I have already discussed the derivation part of the inverting amplifier. Just you need to find out the value of the feedback current I1. So, what will be the current flowing through this capacitor C? It will be current I1 will be C into dV by dt, and this dV by dt is now it is VA minus V naught upon dt, right. So, from there when you further rearrange the equation, then the output voltage V naught will be minus 1 by R1C integration of V in dt. So, this is the time domain equation. When you take the Laplace, then this integration it will be replaced by 1 by S. So, the output is the integration of the input. Now, you can see that this integrator is it acts as a low pass filter actually. The reason is, just refer this frequency domain equation, let us say this equation is x, just refer this equation x minus 1 by SCR1, right. Now, to understand that how it is acting as a low pass filter. So, in low pass filter what happens, the low frequency signal is passed and the high frequency is blocked, is attenuated, right. So, just refer this equation x, and by referring this equation x, if S equal to 0, S equal to j omega, if frequency is 0 means low frequency, then your gain will be V naught upon V in, it will move towards infinite, and if S equal to infinite means frequency is very high, for high frequency your gain will move towards 0, means that at low frequency we are getting higher gain, at high frequency we are getting lower gain. From here we can understand that it is this integrator acts as a low pass filter. But of course, there is a issue in this integrator also. The issue is that at low frequency, since the gain is moving towards infinite, so it becomes unstable also. So, to make it stable, we connect an additional resistor in the feedback path, that is called your practical integrator. The circuit which I have discussed here, this is the ideal integrator, right. So, The point is that in integrator it acts as a low pass filter. Next one is differentiator. Differentiator is a circuit which differentiates the input signal. It mainly utilizes the inverting configuration of op amp. So, to design this differentiator circuit, just interchange the resistor and capacitor of the integrator, right. So, since we are utilizing the we are utilizing the inverting configuration of op amp, it means that the non-inverting terminal will be grounded. Now, at the input side there will be a capacitor, in the feedback there will be a resistor. Just interchange R and C in the integrator, we get this differentiator circuit. This is your input signal V in, this is the output voltage V naught. Let us see, this is capacitor C, this resistor is R. Now, again this is the inverting configuration of op amp. So, it will be V naught upon V in, it will be minus of feedback impedance upon the input impedance, that is the voltage gain equation for inverting configuration of op amp. Now, see what is the value of Z1 here? Z1 is now capacitor. So, Z1 will be 1 by SC. What is Z2? Z2 is R. Z2 is R. So, V naught upon V in, it will be equal to SCR with minus sign. Minus sign is coming because this is the inverting configuration. Input signal is applied at the inverting terminal, right. Now, you can see that now S term is in the numerator, it means that differentiation. Differentiation means S term, it should be in numerator. This is the frequency domain equation where S equal to j omega. You can calculate the time domain equation also, right, just by doing the same process. Considering this is node A, considering the op amp is ideal, if the op amp is ideal, the current entering the op amp is 0, and ideal op amp, for ideal op amp open loop gain is infinite, means we are going to consider the virtual ground concept. Virtual ground means if the non-inverting terminal is connected to ground, it means that the voltage at the node A, it will be 0 volt. So, if the current flowing through the capacitor is I, the same current will flow through the feedback resistor I. Again apply KCL, Kirchhoff's current law at node A, and calculate the value of V naught upon V in, following the same procedure which I have already discussed in integrator and in inverting amplifier. And after doing this, the V naught equation, it will be equal to minus of RC dV in by dt, dV in by dt. So, the output voltage, that is the differentiation of the input signal, if we take the value of RC product equal to 1, right. So, d by dt it can be replaced with S. So, after all we will get V naught upon V in is equal to minus SCR. Now, see this differentiator, it acts as a high pass filter. In high pass filter, the high frequency component is passed and the low frequency is blocked. We can understand it. Now, see by considering this equation, if S equal to 0, then your V naught upon V in will be, it will tend towards 0, the gain will tend towards 0. If S equal to infinite, then the gain will move towards infinite. S equal to 0 means low frequency, S equal to infinite means high frequency. So, for low frequency your gain is moving towards 0, for high frequency gain is moving towards infinite, means at high frequency we are getting more gain. So, it means that it will act as a high pass filter, your integrator that act as a low pass filter. High pass filter, it act as a differentiator circuit, it acts as a high pass filter, right. Now, see one more thing, for high frequency, if we use differentiator at high frequency, since the gain is moving towards infinite, so it may become unstable also, it may become unstable also. To stabilize, we use practical differentiator. So, the circuit which I have discussed here, this is called, this circuit is called ideal differentiator, fine. So, in this class I have discussed about inverting configuration, non-inverting configuration, application of inverting amplifier, that is the adder circuit, application of the non-inverting, that is the voltage buffer. Then after that I have discussed another application of inverting and inverting amplifier, that is the integrator and differentiator. So, we have seen that just by using resistor and capacitor in the feedback path and in at the input side, we can use this operational amplifier for different applications in closed loop configurations. Like we have seen that we have designed summer circuit, adder circuit, voltage follower circuit, integrator, differentiator. Similarly, if we use diode in the feedback path, then it will become log amplifier. If we use the diode at the input side with the resistor in the feedback, then it will become anti-log amplifier. So, that is the main advantage of op amp in closed loop configuration, especially in negative feedback. Fine. This is the reference. Thank you.